Okay, so I'm gonna give you two pieces of theory, okay? Maybe one in this video and another one in another video. And the inspiration for those pieces of theory are that they're the best two solutions for question 5. Does that make sense? Okay. And the amazing thing about the solutions is it doesn't actually spoil the problem. Like, you can still go and do the problem at home. These two solutions have nothing to do with how you're going to do the problem normally, okay? So these two solutions are definitely kind of like more on the, like, it's more like a hack than the intended solution to the problem. Does that make sense? Okay. But they're good for us to learn some theory that we want to learn anyway, okay? The first piece of theory we want to do is called vectors. Have you heard of this? Vectors? So vectors is actually in the extension 1 HSC course.
Physics.
And it's in physics, okay? And it's okay, and when you get and extension 1 is like 2-dimensional vectors, extension 2 is 3-dimensional vectors. Okay. Yeah, extension n is n plus 1-dimensional vectors. But like, what are vectors? Okay. So in physics, they tell you, and if you want a reference for something close to what we're discussing, it's close to the end of the purple book. Okay. So there's a section in the purple book. So what are vectors? According to physics, vectors have a magnitude,
yes, they have a magnitude
and direction. Yeah. And as with all statements in physics, it's like not true, okay? Because the zero vector does not have a direction, okay?
Isn't it like BA plus AC equals BC or something?
Yeah. So in maths, and not school maths, just like general maths, vectors are stuff that you can add and scale. Yeah. Does that make sense? So things for which addition makes sense and scaling makes sense. Okay. Yeah. Okay, and then so that's kind of more philosophical. And then what is so in the physics, they're the same magnitude in the same direction, they're the same vector. Yeah. Here we haven't really said what makes them the same. Okay, so let's focus on 2-dimensional vectors, okay? So this is a bit of a cheat, but you can put an x and y axis on the plane, right? And you can have a point, and I can call this point like A comma B. Actually, that's not the greatest choice of letters. I call another point C comma D, yeah? Okay, so I can think of these points as vectors in the sense that I can add them and scale them, okay? So if I was to add A, B, and C, D, I would get another vector A plus C, B plus D. Another point, yeah? Okay, somewhere. Okay, and scale, scale also means you can scale by negative. So scaling is kind of like you can have some number, a real number times A comma B, and then what's defined to be is just lambda A, lambda B. Yeah, so it's the obvious definition. Okay, does that make sense? Okay, but of course, so this is just the making of points in the plane into sort of a vector space. So you might actually call this a vector space instead of vectors. Like vectors are like the things in the vector space, right? Okay, but then what's commonly called vectors is these arrows. Okay, so what they do is they, instead of saying the point, they make this arrow. They think of these arrows as vectors. Okay, and how do you define the arrows? Well, I guess you just define them as literally like straight line segments which are directed. Yeah. Okay, and we say that two arrows are the same if they have the same length and they're parallel, right? Or they're both like the zero vector. Yeah, have no length. Okay, how do these arrows correspond to the points? Well, what you do is like, so the general definition might be like the arrow that joins 2 points together is the difference of the points. So this is C minus A and D minus B. Does that make sense? Okay. So I said you could add and scale, but that also actually means you can subtract. So when you say add, it usually also means you can subtract. And sort of the way to get that is you can scale by -1 and then add them. So that's the same as subtracting. Does that make sense? So like if you want to add, if you want to do these two, you want to subtract this from that, you just scale this by -1, and then you add them. Okay. So scaling by -1, and then what happens? How do these operations correspond to the arrows? Well, so obviously the origin is 0, 0, right? So this arrow actually corresponds to this point. So this is called the position vector. So the position vectors are the ones that start from the origin. Okay. Okay, and then if you times a vector by -1, it's the same vector but going the other way. Okay? And if you scale it by a positive number, it just gets longer. Does that make sense?
By that number.
Okay, and then there's a nice little lemma, which I'm probably not going to prove, but leaving here. There's a nice little lemma which basically says that if you make a parallelogram, then this is the diagonals are the difference in sums of the vectors representing, you know what I mean? So for this vector and this vector, their sum is the diagonal here and the difference is this. Yeah? Does that make sense? Huh? What? So like this sum here, right? That corresponds to this point, yeah? At the end of the diagonal. And the difference corresponds to this vector, yeah? So this corresponds to that, yeah?
It's just adding and subtracting.
So the sum is this vector. So that's the sum. And that's the difference, yeah? So this is called like the parallelogram law or something. I don't know, but it's not called the parallelogram. It's something to do with parallelogram rule. Okay. So if you draw a parallelogram, then the sum and the difference are on the diagonals. That's just a quick way to remember it. Okay. Another way to kind of remember it is like, this vector here. This vector here is equal to this vector here, right? Because they're equal in parallel. It's parallelogram. Yeah. And displacement is a vector, right? You know what I mean by displacement? Displacement is like going somewhere but with a direction. So distance is just going how far. Displacement is like going somewhere specifically. Yeah?
Having two points
so obviously if you displace yourself from here to here, right? And then you displace yourself from here to there, then your overall displacement is you've displaced yourself from here to here. Does that make sense? So that's kind of like a nice example to add vectors naturally, yeah?
Assume you're walking.
Yeah. Okay, but a very nice consequence of this is like if you have two vectors and you want to say they're parallel, okay, then the condition for them to be parallel is that one is a multiple of the other. Does that make sense? So like because scaling makes it longer, right? Or in the other direction, yeah? And vectors can translate freely. So if they're parallel, then it can just go onto the same line, right? And then it's just scaling. Does that make sense? Let me state that again. So two vectors. So a vector, let's call this v, and another vector u. They're parallel, yeah? If v equals lambda u for some lambda that's real. Does that make sense? Yeah? Okay, in the book and in your course, there's like dot products and stuff as well, but we don't care about that right now, yeah? Okay. So if we had the cross product for three-dimensional vectors, it could be cross product equals 0 or something, but we're not talking about that right now, okay? Okay. So the question is, I'll give you a few minutes to think about this, maybe 3 minutes. So if we do this problem here, right? So I have A, B, C, D. You see? This is A, B, C, D, right?
Yeah.
And you take the midpoint, you find the midpoint, yeah? If that's the case, okay, we're trying to prove that AB is parallel to CD, yeah? Does that make sense? Okay, I'll give you a few minutes to think about it, but I believe this is the best solution to this problem, even though it's by far like not the intended solution. No? Do you see it?
It's no, that's what we just said.
Oh, okay. By the way, so you know how the coordinates x and y, right?
Yeah.
And the vectors, it's a very similar thing. Whenever you start a problem like this, you need to basically the only real choice that you need to make is where to put the 0 vector, or where to put an origin or the x and y axis. Does that make sense?
Wait, what are we trying to do?
We're trying to prove AB is parallel to CD,
Okay.
and M and N are the midpoints.
Okay.
Wait, you did this in the actual exam.
Oh, yeah.
Did you skip it?
No.
You solved it.
No.
Wait,
Wait,
who's that?
You
Who's
just
that?
went all in on it?
No.
Wait, you can't. There's like one of those has to be true. You can't say no to all
I
three.
don't have to go all in on it.
You solved the question and you
Wait, but
did
you
not
can
solve
either skip it.
Yes, which is going 0 in on it.
Oh, okay.
For like some amount.
That's what you mean. Okay. So you kind of tried it for a bit, then skipped it.
Huh?
May I have some substance?
Wait,
Ah.
Michael, I wanna ask. If there's a circle and there's a triangle, A, B, C, and there's like an angle bisector intersects here, D, what's D in terms of ABC in complex bash?
The complex bash.
No, I'm doing the question that I solved.
Oh, I mean, what you can do is you can make so you can make C instead of making it little c, you can make it little c squared. You can make little b squared, and then.
Is it like
and then-
BC, negative
and
BC?
D, yeah, D is plus or minus BC. Yeah.
Oh.
Yeah, because it's the leaves.
Alright, yeah.
Oh yeah, first principles of complex bash.
Thanks.
So where would you put the origin, guys? That's kind of the main question I'm asking you.
The origin.
I'll do the rest for you. I'll do all the manial labor for you.
Where the diagonals meet on M and
Yeah, can you see that would be a great choice for origin, right? So it's literally all the points everything comes out of that point, right?
every point.
So it's literally the origin of all the lines, right? This is a great choice for the origin, yeah? Does that make sense? Okay, so now let me show you how vectors absolutely crushes this problem, okay?
Okay.
Check this out. So you draw this vector here, yeah?
Yes.
That is little a, yes?
Sure.
Okay. Notice how C is in the same line with it. Yeah, so we can make that negative lambda a, yeah? That makes sense? Makes sense? So C is negative lambda a, yeah?
Okay.
Lambda is positive, yeah? You can make B
Little b.
little b, yeah?
Yeah.
Okay, and then D
It's negative lambda b.
is negative mu b, yeah? It could be a different constant, yeah?
Okay. Sure.
Okay,
What did you
don't
just call it?
mu.
You?
Like lambda's L in Greek, right? And then mu is M.
Oh, about.
Okay. So I'm out of letters, so hopefully there's no.
Density or something?
density. Oh no. We're just using it's like any letter. It's like A or B. You know? Just arbitrary letters. They don't mean anything. It's not physics. All right. Okay. Now what about M? Do you know what M is? Do you guys learn midpoint in coordinate geometry? So midpoint is literally like if you have X and Y and like U and V, right? The midpoint is X plus U on 2, Y plus V on 2, right? So you might learn this in school even, okay? So M is just literally half A. Wait, why am I putting A on the bottom? It's A plus B on 2, yeah? Yeah? And N, okay. Okay, so this is kind of the annoying part. Is negative nu of A plus B on 2. That makes sense? Because it has to be in the same line, but it's also C plus D on 2, right? Yeah? That makes sense? So N is the midpoint of C and D, so it's C plus D on 2, right? But it's also on the same line as M, right? So it has to be a multiple of M. So it's negative a multiple times A plus B on 2, right? Yes? But what is C plus D on 2? Well, C is lambda A. So this is negative lambda A plus mu B on 2, right? Okay, does that make sense? Okay, so the main thing here is you got to notice if it's just the same number of A's and the same number of B's, right? And we're timesing it by a constant, yeah? Then it's not going to be easy for it to be a different number of A's and a different number of B's here, right? So that's the heuristic, that's the idea, yeah? Okay, but to prove it, to prove it, you can just say, oh, if these were, so you can just solve the equation, right? So you cancel the negative signs, yeah? And then you collect the A's. Yeah, you cancel the negative and the 2, yeah? So you cancel the negative and the 2, yeah? And then you collect the variables. So you get lambda minus nu times A plus or equals nu minus mu times B, right? That makes sense? So that means A is a multiple of B, right? Yeah? So A is a multiple of B, but for A to be a multiple of B, it means B has to lie here, right? Or here. Yeah? So B can't lie on the diagonal AC, you understand? Yeah? So the only way for this equation to be true is if both of these are 0. Yeah? So then lambda equals nu equals mu, yeah?
Oh,
That makes sense?
what the?
And then some people are seeing into the next step already.
So the question is done.
The question's done. So now you want to see if CD is parallel to AB, right? So you do C minus D, right? Equals, and we know lambda and mu are both nu, right? So it's negative nu A plus nu B, right? Plus a nu B. Okay, and then minus nu A minus B. See?
We are done.
So they're parallel, and we're done. So the crazy, like, think about it, right? This solution takes literally a minute to write up, and actually, it's like a minute to solve and write up, yeah? And there were people got stuck on this for like 2.5 hours and had to skip. I'm not saying that was you.
1 minute.
That was pretty cool, right?
Yeah, that's pretty cool.
Okay, so I'll let you be the judge. So if you think this solution's better or this other solution, so I'm having an argument currently with some people. They think their other solution's better. But how can you be better than this? I'm like,
Unless there's some.
How about my trick?
this is complex bash.
How about my trick?
Oh.
So it's like these are complex numbers. You're just not multiplying them.
And there's no u that's
Yeah, so there's some people think this other solution is better, okay?
Yeah.
And they're saying it took like, it's like, oh no, this other solution is better. It only takes a minute. And I'm like, this only takes 30 seconds.
Oh
Okay,
wait, do you know that trick? It used 40 minutes.
Yeah. More Sussons. Okay, give me a second.